Hello, and welcome to this video from NHOP Technologies, giving a short introduction to batched sparse codes. We will start with a brief look at TCP, and then we will turn to random linear network coding, and finally we will come to batched codes. Let's begin with an overview of how TCP works over a single link. TCP accepts a data stream from the source and divides it into segments. Each segment is sent in turn, and an ACK message is sent back when the segment is received. This ACK message sets a window size, which in this case allows the source to send 4 segments in a row without receiving an ACK for each individual segment. But if there is no ACK at the end of this window, then the source automatically slows down the flow rate by reducing the window size by 50%. The source then has to resend all the segments in that window, in this example segments 2 to 5. The key points here are that TCP requires confirmation that every segment is received over each link in a network, and that retransmissions slow down the data flow. Let's consider TCP over a wireless network with 2 hops, both of which will drop some data packets. All is fine when a segment gets to the destination without being dropped, but segments dropped by either link cause retransmissions, and they can quickly accumulate and start to dramatically interrupt the overall flow. It's easy to see that in this scenario the latency will go up and the throughput will go down. To recap, TCP works well over wired networks with low latency, but it becomes inefficient in networks that have many lossy or high latency links. Network coding, however, does not work in this way. So let's take a look at random linear network coding. In this approach, before transmission, the data segments are randomly combined together into packets using linear algebra. We can make an almost infinite number of these linear combinations, all containing some useful information about the source data. This means that we can choose any packets at random, and when we have enough of them, the group of packets can be decoded to reconstitute the original data. So when a packet is dropped, we just have to wait for another one to replace it. Let's see how this works in the 2-hop wireless network that we looked at earlier. The source starts by randomly combining data segments into packets, and as each packet is created, it is sent over the first wireless link. As with TCP, some packets will be dropped, but transmission of new packets continues without the interruption of waiting for any acknowledgements or resending dropped packets. It doesn't matter how many packets are dropped, so long as in the end, the destination receives enough packets to be able to recreate the data. When a full set is received, the destination sends a stop message back to the source and starts the process of decoding the data packets. So far, this illustration has assumed that the data packets are passed straight through the intermediate node. But in practice, we can also recode the packets when they are received at each relay. Recoding improves the packet drop in the following link, making networks that have many links in series a practical possibility. We can therefore see that random linear network coding has some important advantages over TCP/IP. There are no acknowledgement messages and no retransmissions. This makes it suitable for networks having lossy or high latency links. There is no need to know the topology of the network and to devise a routing path through it. Any route through the network will work. Multicast is easy to implement. Recoding at intermediate nodes can be used to improve packet drop over lossy links, and that allows multiple hops, each one over a link with high degrees of packet drop. However, there are also disadvantages. The RLNC encoding and decoding process is complex and therefore requires significant computing and storage resources at the intermediate nodes and at the destination. The size, the cost, and the power consumption of these devices is quite high, and which is particularly important when considering how to implement IoT applications where devices may need to be very small and even battery powered. And so we come to batched sparse codes, or BATs, which was designed to improve upon random linear network coding by making substantially lower demands on computing and storage resources. BATS has also been optimized for networks where multi-hop wireless links can offer cost-effective solutions without a dramatic loss of throughput. Let's take a look at how BATS performs this coding process, which is in two steps. First, there is an outer code, and then an inner code. The outer code begins by pre-coding the data segments to provide erasure protection, after which a matrix-generalized fountain code encodes the segments into batches. This is followed by an inner code which combines the coded segments in each batch using linear network coding. As each batch is prepared by the inner code, it is transmitted sequentially through the network. Each batch is recoded individually at intermediate nodes, the size and scope of each batch demanding less computer power and less storage capacity. In summary, BATS is optimized for multi-hop networks. The coding complexity and data storage requirements are modest, and the latency introduced by BATS coding is low. This makes BATS an ideal solution for video streaming, especially if the network path involves more than one wireless link. It is also very suitable for IoT applications. And the nature of linear coding means that the data packets are in effect encrypted, so there is built-in security against eavesdropping as the packets cross the network. Finally, and most importantly, BATS offers near-optimal throughput, both in theory and in practice. Looking first at the theory, this chart gives a comparison between TCP/IP and BATS codes when applied to multi-hop situations. In this model, each sequential link is assumed to have a packet drop of 0.2, meaning that 20% of the packets will be erased over each link. As can be seen, the throughput of TCP/IP drops very quickly, such that after 10 hops, the throughput is just 0.1, and this reduces to nearly zero after 20 hops. By comparison, the BATS throughput stays above 0.7 all the way to 50 sequential hops. Turning to practical implementations of BATS, a very important feature is that there are no changes to the bottom two layers in the TCP stack, the link layer and the physical layer. So for example, if we look at how TCP operates over a Wi-Fi link and compare it to BATS operation, you can see that the differences only affect the transport layer and the network layer. This is important because it means that any enhancements to the 802.11 specification can be deployed in the link and physical layers, and the BATS codes will work in just the same way. Therefore, when standard Wi-Fi achieves higher bit rates, those benefits will become available in any BATS system. For real-world proof of BATS in practice, a pilot system has been built in Hong Kong based upon a string of 30 standard lampposts. Each of the lampposts were equipped with a BATS box in the base. These boxes give environmental protection to the IP65 standard, and they are small enough to be fitted inside the base area of most lampposts without any modification. Each BATS box contains two Wi-Fi transceivers, which can be programmed for either 2.4 GHz or 5.8 GHz operation. In the pilot system, the lampposts are interconnected at 5.8 GHz. There are two MIMO antennae higher up the lamppost and connected by feeder to the BATS box. MIMO, which means multiple inputs, multiple outputs, is a good example of a major Wi-Fi enhancement introduced via 802.11n. Before MIMO, a Wi-Fi link could only use a radio channel to send one stream of data. But MIMO allows several simultaneous streams to be sent over a single radio channel, providing substantially higher data throughput. Currently under 802.11n, up to 4 simultaneous streams can be sent over one channel. The next generation, 802.11ac, allows up to 8 simultaneous streams. This and any other future Wi-Fi enhancements will be available in a system that uses BATS coding. In the pilot system, the BATS box in the first lamppost in the chain has an Ethernet connection through which test data streams are sent along the chain of lampposts. Measurements of the data throughput along the chain and at the 30th lamppost have confirmed that BATS coding delivers in practice what has been calculated in theory. This efficient and cost-effective solution can be used to connect a variety of services to connected lampposts, including local Wi-Fi at 2.4 GHz, traffic monitoring, air quality measurement, weather conditions. These and many other services are now at the planning stage in many cities around the world, and lampposts are generally seen as an obvious way of delivering them. However, it is expensive to lay fibre to every lamppost, and it usually involves a very time-consuming process of obtaining wayleaves to allow digging in the fibre to each post. Wireless connectivity by BATS, on the other hand, is fast and cost-effective. The frequencies used are from the license-free bands of 2.4 and 5.8 GHz, so there is no requirement for the complicated process of applying for specific frequency licenses. In addition to the current BATS box product, development of a custom field programmable gate array chip is planned in 2021. This will allow BATS coding to be embedded inside devices such as video cameras, therefore extending the ease of deployment. For a more detailed discussion on the benefits of BATS networking, please contact us via info@n-hob.com. Thank you.